So in the previous video, we discussed how we can qualitatively categorize acids as strong acids versus weak acids, right? We have a set of 6 strong acids, and anything not in that set is a weak acid. But we can actually mathematically express how strong they are with a Ka. So a Ka, it's exactly like a Kc, so an equilibrium constant, but specifically it's for acids. So it's an acid ionization constant. And we can measure how strong acids are based off of their Ka, because all a Ka is, like I said, it's a setup for a Kc or a Qc. So we have the products divided by our reactants, right? So here we have our products, which are our hydronium and our conjugate base form from the acid. And then also for our reactants, obviously we have our acid. Notice that water is not included here because it's a liquid. Remember, solids and liquids are not included in equilibrium constants. So the same thing applies here. So we call this, again, acid ionization constant, Ka. The little a stands for acid. The bigger the Ka, the stronger the acid. The bigger the Ka, the stronger the acid. So let's think about why that is the case. If you have an acid, any acid, and let's say it's a strong acid, right? We talked about how a strong acid completely ionizes. It completely breaks up into protons that then react to form, your hydronium with the water. But anyway, it will completely ionize to form hydronium and then the conjugate base. Because it's completely ionizing or coming very close to that, then you will have a lot of this in solution, right? And because you have a lot of that in solution, it's a product, right? So if you have a lot of these in solution up here on the numerator, or very high numbers up there, by whatever number you divide by in the denominator, you're going to get a very large number here. So if you have a lot of products, you get a large Ka, meaning you had a very strong acid because it dissociated very well. Here are some examples of different acids along with their Ka values. These are actually monoprotic weak acids. So we're going to discuss what protic means, but honestly all it is, just a really quick explanation of it, is mono, one. Protic means how many protons can come off of it. So for example, here we have 1 proton that can come off and act, for it to act as an acid. So here we're just showing a bunch of different acids, their Kas, and how they're different from each other. Notice that all of these Kas have values with negative exponents. So the smaller that value of that negative exponent, then the larger the Ka. So the smallest Ka is down here. So this is a very weak acid. Compared to this one up here, it's not as weak. So remember how we talked about how pH is useful to take a concentration and turn it into a number we can use, right? So if we have a hydronium concentration of 1 times 10 to the negative 5th, converting it into the pH or calculating it into the pH is much easier, because what you will get is a simple number, right? We go from 1 times 10 to the negative 5th to 5. It's a lot easier to work with. And you can actually do the same thing with a Ka. So we just discussed Kas on the previous 2 slides, and they can be values, ranging from very small value to slightly bigger. But for example, we saw something that was around this range, right? So if our Ka is that, right, that's a really, really small number. We can take that really small number and we can calculate something called the pKa, and then we get a more normal number. So we would basically take the exact same calculation that we do for pH and do that for pKa. So the pKa for this would be 10. So the calculation is right here. And again, same idea, where you take that number that it's raised to, that is your pKa. So You can also calculate it for bases. So that's what pKb stands for. So for any Ka that you calculate, you can also calculate the Kb. It's the exact same thing except for a base. Here the trend is the stronger the acid, the smaller the pKa. So here, right, this particular example, the Ka was 10 to the negative 10th, the pKa was 10. The Ka is telling us that there is very little product in solution, meaning that the acid did not want to ionize, meaning it was a weak acid. And when you look at the pKa, it has a very high pKa of 10. High pKa means weak acid again. So the stronger the acid, the smaller the pKa. Here we have a very weak acid, right? Larger Ka, smaller pKa, they're inverse to each other, right? Because it's the log. The stronger the base, the smaller the pKb. So high Ka value tells you one thing, and pKa is like the opposite, the inverse of it. And the same thing for Kb versus pKb. So let's go back and think about how water is present in any acid or base solution, right? Or any, neutralization reaction, for example, if you have that. You have water there. So how is water contributing to the concentrations of hydronium and hydroxide? So water can contribute to both of these, right? Not only is it the acid and the base contributing to these, you also have the water. So for a strong acid or base, the contribution of the water to the total hydronium or hydroxide is negligible. So you don't have to worry about those for strong acids and strong bases. This is the case because for strong acids, you have so much of your product of that hydronium being produced that it shifts the Kw equilibrium, right? Kw has to do with water and the concentrations of hydronium and hydroxide in it. Because you have so much hydronium from that acid shifting this equilibrium to the right, whatever amount that you produce of hydronium from your water is like insignificant. It's just negligible. And only in very, very dilute solutions will water and its contribution to hydronium and hydroxide affect it. But for the most part, for strong acids and bases, it's negligible. So in general, when you have a basic monoprotic, meaning it only has one proton to give off right here, when you have a basic monoprotic strong acid, the concentration of the acid will equal the concentration of hydronium. For polyprotic acids, meaning you're going to have more than one of these to be given off into solution, the other ionizations can generally be ignored except for H2SO4. This second ionization cannot be ignored. So in general, if you have a concentration of your acid, for example, the strong acid 0.1 molar HCl, the amount of hydronium will be 0.1 molar. And when you take the pH, when you do the pH calculation for that, it'll be 1. For a strong base, the OH concentration is determined by the number of OH polyatomic ions that you have for the base times the concentration of the base. For bases that have more than one lone pair available, right, because the requirement is you have to have a lone pair to accept a proton. For most of these, when you have multiple lone pairs available, only one lone pair can accept the H. The other ones can generally be ignored. So kind of a similar idea here. So if you have 0.1 molar of calcium hydroxide, we are going to take the number of OHs, meaning 2, right? It has 2 right there, times the concentration, which is 0.1 molar. So we multiply it and you get 0.2 molar. And then when you take the pH of that, you get 13.3. So how do we find the pH of a weak acid? So with weak acids, there is a little bit more of calculations because for weak acids, we don't have a complete ionization the way that we do for strong acids. We only have a partial ionization. So how do we determine like how much of that is ionizing, how do we overall get pH from this, right? So we're going to have to do equilibrium problems for these, and you will see some examples either in this video or in the one right after. There is another way we can measure the strength of an acid, and the way we do this is to determine the percentage of acid molecules that ionize when dissolved in water. This is called the percent ionization. The higher the percent ionization, the stronger the acid. And the way we calculate this is the molarity of ionized acid divided by the initial molarity of the acid, right? So it's like the final state, right, divided by the initial, and you see the overall percentage. So it's like the part over the whole, the end result divided by the starting, right? So this is how we summarize it: the molarity of our hydronium at equilibrium divided by the molarity of the acid itself initially before it started ionizing. So in this example, we are calculating the percent ionization from a pH. So we know that percent ionization is equal to, I'll just write percent, is equal to our hydronium at equilibrium divided by our acid initial times 100%. In this problem, we are given the concentration of the acid and we are given a pH. So the good thing here is we're straight up given our concentration of our acid. We have this for sure. The only thing we don't have directly is the concentration of hydronium. This right here. We have this. This is good to go. So what we have to do is think about how we calculated this pH in the first place and whether that can help us get the concentration of hydronium. So remember, pH is equal to negative log of the concentration of hydronium. And that's horrible, but you get the point. So we do have the concentration of hydronium. It's just hidden in there in that pH value. So that is our unknown. So we're going to set our pH equal to negative log, equal to the calculation for pH. And in order to take away that log and isolate our concentration of hydronium by itself, is we need to take the anti-log of our pH value. So again, this is something called the anti-log. The anti-log will be that first we take away that negative sign. So we're going to multiply both sides by -1, multiply both sides by -1. What this does to our right hand side is take away that negative. Now we have negative 2.09 equals, whoops, the concentration times the log. So log, now it's positive, H3O plus. To take away that log, we need to raise both sides to 10. So whatever numbers you have, you're taking those and putting them as the exponents for 10. So on this side, we also raise it to 10. Raising 10 to this entire value here and this entire value here, it'll cancel this part out right here. And then what you're left with is H3O concentration and 10 to the negative 2.09. So that gives us the concentration of H3O overall for our hydronium. So from this, you should get 0.0081 molar. So now we have all the concentrations we need, and we are going to go ahead and plug this in. So we have our concentration of hydronium up here at the top. And then here at the bottom, we have our concentration of the acid to begin with. So weak acid. And then when you calculate that out, we should get 6.5%. So in that way, you can determine, okay, how weak is this acid actually? And it's actually pretty weak, only 6%, or it's about 7-ish if you round it. Only about 7% of this acid actually ionizes and puts out those protons into solution. So what about for the case when you have a mixture of acids? How will the pH be affected by these two? So if you have a mixture of a strong acid with a weak acid, the overall ionization of the strong acid is what provides all the hydronium necessary to shift the equilibrium. And overall, the amount of weak acid that contributes to the hydronium is negligible. For mixtures of weak acids, you only necessarily consider the stronger one, and it's kind of the same idea as for a strong acid and a weak acid. One of them is going to be negligible. What about bases? How do bases compare between strong bases and weak bases? So just to recap, stronger bases, what they're going to do is they will more willingly accept protons. Remember, bases, Bronsted-Lowry bases, have to have a lone pair in order to accept these protons. So if we use water as like the standard acid, then we can compare and see how willing they are to accept those hydrogens, those protons. For ionic bases, practically all the units are dissociated into hydroxide. So this means they are strong bases, they are strong electrolytes overall. If you have multi-hydroxide strong bases, for example, the one we discussed earlier that had 2 total OHs or 2 hydroxides, these also completely dissociate. And here we just have an illustration. So if we have NaOH in solution, it will completely dissociate into sodium cations and hydroxide ions. In weak bases, only a small fraction of the molecules accept the protons. In other words, not all of them will take those protons in order to produce OH, right? Whenever bases take protons from whatever acid is in solution, for example, if we say water, then you end up forming OH minus. So even if the base doesn't necessarily dissociate to form that OH minus, it will cause it to be formed. So weak bases, weak electrolytes, most of the weak base molecules will not take that proton from the water, and the concentration of hydroxide will be a lot less than the weak base. So finding the pH for these is similar to finding the pH of a weak acid. We're going to have to do some calculations that involve ice tables. So we can also calculate the Kb. So it's the same idea as the Ka, except for a base. And it helps us determine, base strength. So here we have just a general reaction of a base, with that lone pair reacting with water, and it overall produces OH minus in solution, and you get that conjugate acid from that. So to calculate it, again, we would take the products, which are right here, products, and divide them by our reactants. A larger Kb means a stronger base. Here are some common weak bases. So we are looking at, for example, ammonia. That's a very common one that you actually deal with in your life. Sometimes if you use Windex, it has ammonia in there. The Kb for that is 1.76 times 10 to the negative fifth, so it's somewhere in between. A very weak base, which is probably something you've never worked with, is aniline. You can see that it's a lot smaller, right? The smaller it is, that means the weaker the weaker acid or base. So over here is very weak. Over here is stronger, right? Not strong base, but stronger in this, relative group of weak bases. Pyridine is some really nasty stuff. I've worked at that in lab. It's just the most horrible possible smell you could ever smell, and it burns and it hurts and it gives you a headache. So hopefully you guys never have to use it. And then on here, notice that we have some amines, and obviously ammonia is an amine as well, but amines have nitrogen groups. And the reason that these are bases is because they have lone pairs. So, oh, and also pyridine. So the overall structure of amines tells us that we have lone pairs on those nitrogens. These are nitrogens right there, those blue ones. And this is why you have kind of this family, right, that can be a base because you have those lone pairs. So this is just a nice visual comparing these different weak bases and how they all have those lone pairs available to take the protons. So we're going to end off this video actually with acid-base properties of ions and salts and how these can be categorized as bases versus like its conjugate and so on. So salts that contain the cation of a strong base and an anion that is the conjugate base of a weak acid are basic. So this may seem a little convoluted before you really dig into it and see what this means. That's okay. So let's say we're looking at sodium bicarbonate. This overall is an ionic compound. It has a polyatomic ion right here, and it has a metal. So overall, and this is a polyatomic anion specifically. So overall, this is an ionic compound, which we generally term salts, right? How do we determine if this is basic or acidic? So whenever you have a cation, this is the cation, our sodium, that is the cation of a strong base. In other words, what are the strong bases? If you go to your list, you will find that the strong bases include NaOH. So this is the cation of a strong base right here. And an anion that is the conjugate base of a weak acid. So this comes from a weak acid. In other words, H2CO3. Remember, of the strong acids, there's 6 of them. And that list does not include this, meaning it's weak. So this in particular, HCO3 minus, is actually the conjugate base of this weak acid right here. So you have to kind of go back and think, okay, these separately, what are they? If the anion comes from a weak acid and the cation comes from a strong base, then you have a basic solution overall. So just giving you a second probably to kind of look at that. And then the opposite case is whenever you have an ionic solution that is acidic. So in this case, we're looking at ammonium chloride. Ammonium chloride is the conjugate acid of a weak base. So instead of the cation of a strong base, we have the conjugate acid of a weak base, ammonia. And then chloride is the anion of a strong acid, HCl. So again, you have to split them up and think, okay, what is the conjugate acid of this? And where is this anion coming from? So you can actually consider every single anion as a conjugate base of an acid. And because of this, every anion can be a base, right? If it can be thought of as the conjugate base of an acid, then it can act as a base. So here we have just a general ion A minus reacting with water, and we get an acid and OH in solution. The stronger the acid, the weaker the conjugate base. So this is an idea that will help you for the further calculations we will do. But if you have an anion that is the conjugate base of a strong acid, you will have neutral pH. So look at the products and we can see why. We end up forming HCl from this just anion kind of by itself acting as an acid, and it is the conjugate base specifically of HCl. So because of this, whenever you throw it in water by itself and you let it react with the water, it will form HCl and OH. And if you think about it, these cancel each other out. So overall, you end up having pH neutral. If you have an anion that is the conjugate base of a weak acid, you will have a basic solution, because overall, this forming from this anion, this is weak. So not all of it is going to ionize. It's not going to neutralize completely with that OH. So we just mentioned, okay, the stronger the acid, and I'll just write A, then the weaker the conjugate base. So if we look at the equations for both of these reactions, right, the acid going forward and producing hydronium, and if we look at the conjugate base going forward and producing, acid, if we add both of these up in both directions and we add it up, what we get as a net is just 2H2O giving us hydronium and OH. And if you remember, this also had to do with the auto ionization of water and when we were looking at Kw. So if we relate these two, and if you remember hopefully how we would do for determining equilibrium constants from known equations and Ks, remember we multiplied. If you add up these two different equations, what will I do with the equilibrium constants? We learned about how we would multiply these together, okay? So in this particular case, we have the Ka for the acid, and then we have the Kb for that conjugate base acting that way, producing, these products. So when we add these up, what we're going to do is multiply these together. When we multiply these together, if you notice, you will see that the HA cancel each other out. The A minus, which is the conjugate base, cancel each other out. So the acid and the acid, the conjugate base, cancel each other out. What you end up with is the concentration of hydronium times the concentration of hydroxide. What this also equals is the Kw. So now we have this relationship. We have the constant for the acid, and I wrote that wrong. The constant for the acid multiplied by Kb, and that should be a B, equals Kw. So now we can use this information and this relationship to calculate anything, whatever unknown you're looking at. And remember, this relationship right here is inverse. If you have a strong acid, you're going to have a weak conjugate base, and it has to do with this because we know what Kw equals. It always equals 1 times 10 to the negative 14th. So if you increase this, then this has to decrease in order to keep that being equal to that value. So that's where that relationship comes in.